You will be getting a reference sheet. Yes. I will be posting it. I haven't finished it up yet, but you'll be getting a reference sheet with a bunch of info on it. It'll be just like the last one. I might have a little bit more. You still have to do all the work, but I might have more multiple choice just from the perspective of you picking an answer. But all right, problem number 7, chapter 17. Right. It says, from the value of Kf listed in table 17.1, calculate the concentration of ammonia required to just dissolve 0.02 moles of nickel C2O4, which has a Ksp of 4 times 10 to the minus 10th. And oops, what's going on here? There we go. Which has a Ksp of 4 times 10 to the minus 10th. My pen is really, all right. Strange, my little pointer is not working right. All right. Well, in a 1 liter solution, hint, you can neglect the hydrolysis of C2O4 because the solution will be quite basic. All right. So the first thing you needed to recognize here is to be able to draw out the dissociation equation, right? So you're dissolving the nickel salt in water, you get nickel ions plus the counter ion. And your Ksp equation, right, is going to be, because both of these are to 1, so your Ksp is, has both of the first order. So that's the first thing you need to recognize. Then you set that equal to 4 times 10 to the minus 10. So when the salt is just dissolved, you want the C2O4 concentration to be equal to the 0.02 molar. And so when you're going through this, the first thing you needed to recognize is that when you're trying to dissolve this entire solution, right, you're trying to completely dissolve it. So if you're starting with 0.020 moles here, right, you're going to end up, once it's completely dissolved, with the exact same 0.020 moles of the anion in solution, right? Because this is a 1-to-1 ratio. So that's the first thing that you need to recognize. So that you're basically, you need to recognize that you end up with that 0.020. Since we have a 1 liter solution, right? So that's the 0.020 moles divided it by the 1.00 liters, which gives us our, right, is this the 0.020 molar solution. So that gives us our concentration that we see here in the problem. It says then, thus, the nickel 2 plus has to be less than 4 times 10 to the minus 10th divided by that 0.020 molar to achieve the solubility. So what does this mean? First off, I'll go through this, but I'm going to go through it a little quickly because I'm just recognizing from the problem set perspective, this is a KF problem, and I'll go through it. Were you asleep today in class, Brian? Because this is one of the problems that's not going to be on the exam. You're here for the help session, but I told you I wasn't going to give you any KF problems. So at least not from this perspective. But anyway, so you basically, what you needed to do is you needed to just plug in these concentrations into the Ksp equation here. And when you plug in the Ksp and solve for the nickel, that's what this equation is right here, right? So we solve for understanding you need 4 times 10 to the minus 10th for your nickel concentration in order for the, I'm sorry, not 4 times 10 to the minus 10, the 2 times 10 to the minus 8 for your nickel concentration. And that's what you're going to, solve for. So then you're going to basically take this and complex that nickel with the ammonia, and you create this other complex equation. And that complex equation, you then go through just kind of through the traditional, equilibrium constant expression, and you use the table, which has the KFs for these particular complexes. Again, that's table 17.1 to get your KF, and you just do a traditional equilibrium constant expression where now you have your solubilities of all your compounds.
Dr. Barbosa?
Yep.
I had a question about this. How do you know that the concentration of the NiNH3 is going to be 0.020? Because I thought because the KF determines how much of it's formed, it's not going to be formed by the entire molarity of 0.020.
Well, you say, so you're not going to, well, when you're going to make, in the second part of the equation, when you're creating your complex, right? You make the assumption that the complex is completely formed. And we covered that in class, briefly today. So you're going to make the assumption because the complexation between the nickel and the ammonia is has the KF, right? The KF is very, very large, right? Down here it's 1.2 times 10 to the minus 10. So we have a very large formation constant. So you assume all of the nickel is forming, and and that's where your concentration is coming from. Is that what the question you're asking? So you're going to make the assumption that all of your nickel has been complexed and has been formed into this nickel ammonia complex. And then when you go to calculate using the KF, you have your ammonia concentration is what you're going to be solving for right here. So you're going to be solving for the ammonia concentration here. You have the nickel concentration because that's what you calculated from the Ksp equation here, right? This is one of the reasons that I'm not going to be testing you on this, because it's a lot more complex, and since we only covered it today, I didn't want you to confuse yourself. I can keep going through this. I just don't want to waste your time because I am not asking.
That makes sense. Thanks. I didn't know you had to assume that.
Yeah. So anyhow, that's basically how you're working through the problem. Again, I'm not going to give you a KF like this one. I gave it to you in the homework, but because more timing than anything. Because we only covered it today, I didn't want you to go through and waste your time. All right, let's go over another one. Let's see. Let me see something. He's not here yet. Brian, I will come back to number 5 if Jason shows up. He's not here yet, but we'll go on to 4B and C. Freddie. I assume that's problem set 17. He has problem set 16. That was the other section. All right. 4B and C. So buffers prepared by adding 10 grams of ammonium chloride to 250 milliliters of a 1 molar ammonia solution. So the first part was asking what the pH of the buffer was. After you get the pH, which is down here, you then, part B says, write the complete ionic equation for the reaction that occurs when a few drops of nitric acid are added to the buffer. Right. So what you're going to be doing is you have your ammonium chloride solution, right? So, and this is the ammonium chloride solution, right? So you have your NH4Cl, and when you dissolve NH4Cl into solution, right, this is a solid. When you dissolve it into solution, drawing is really bad right now. NH4Cl, and you dissolve this solid into solution, you end up with ammonium ions plus chloride ions in solution, both aqueous. And then you're also going to be adding ammonia, right, NH3, and that's an aqueous solution. So you're adding the ammonium ion plus the ammonia. So your buffer solution is what's shown here, right? Where you have the ammonium ion is in equilibrium with the protons and ammonia. So they're asking in the second part of the equation, if you're adding nitric acid, you have to recognize, first of all, that the nitric acid is going to affect the H plus side of the equation. So the reaction is going to be going in the reverse direction, where now the ammonia that's in solution is going to react with the protons, right? And nitric acid, when you dissolve nitric acid in water, you end up with complete dissociation because this is a strong acid. Right, these are one of the strong acids, so you end up with complete dissociation. Of your ions, and the ammonia is going to react with the protons. The nitrate ion is just a spectator ion, which shows up on both sides of the equation. So you end up basically just adding in the extra nitrate ion that's in solution. So you end up with a nitrate. You end up with a reverse reaction, because remember, the buffer systems can go in both directions, right? If we were to add base, then the base would react with the ammonium ion component and go in the forward direction. But since we're adding acid, we're reversing the equation and going in the opposite direction. Then part C says write the complete ionic equation that occurs when a few drops of potassium hydroxide are added to the buffer. So, right, the potassium hydroxide is the same thing, right? Where we have now, and you take KOH and you dissolve that, right, as a solid. You dissolve that in water, you end up with potassium ions. It's an aqueous solution plus hydroxide ions as an aqueous solution. And in this case, you're going to have your ammonium ion is going to be reacting with the hydroxide to free up, give you the ammonia and water. This particular answer, because your original equation doesn't show the chlorides, you could leave the chlorides out here, and your answer would also be correct just from a balanced chemical equation perspective. Otherwise, the potassium ion is the only spectator that shows up on both sides of the equation. Does that make sense? I don't know if I answered your question. I just kind of explained what was going on. Ready? Oops. Wow, lots more questions. I didn't see. let's see. Okay, for things. Let me read through. There are a couple more questions. I didn't see them all. It's a nice thing to scroll down. Periodic table. You'll have a periodic table as part of the sheets that I'm going to give you. So this time you will have one, and you may need it for one problem. Let's see. Oh, Jason's here. All right. Very good. Let's see. So, all right. So now we can go over number 5. Yes, Dominic, correct. You're not going to need anything. You have so far. Here, I can show you. Let me show you what I have so far for the reference sheet. Here, let me show you the reference sheet. Just everybody's probably wondering so far what I have. Here's the reference sheet to date. And I'll go back to the problem in a second. Right now you have useful equations, right? Kw, pH, pOH, percent ionization, Ka, pKa, the Henderson-Hasselbalch, the relative strength of acids and bases, right? You have your strong acids, your strong bases. Obviously, there are a few more strong acids that we talked about over the, basically having, ClO4, things like that here. And we have another table of common strong acids and bases, right? So I put both of them in here, right? So this is the other table. Dissociation constants for bases, right? These are your table Ds. These are the ones from Appendix D I told you to look at in the past. Your formation constants, they're in here from the past. Like I said, you're not going to need them, but they're there in case you are wondering. Dissociation constants for acids, right? This is the Appendix D table. Then some acid dissociation constants for metal ions in solution. The Ksps are all here. The qualitative analysis sheet that I mentioned today's class. And periodic table. So that's what's there so far. That's currently what exists in the sheet. All right. Back to problem number 5. All right. So problem number 5, this is consider the titration of 30 milliliters of a 0.505 molar solution of ammonia with 0.025 molar hydrochloric acid. Let's calculate the pH after the following volumes of titrant have been added. Right, so the first part of the equation, we haven't added any acid yet. So the first part of the equation is essentially just mixing in ammonia and water. Right, so this is one of the ammonia and water reactions. So when you mix a base, right, in this case, ammonia, let me slide this over here. NH3 plus water reacts in an equilibrium fashion to give you the ammonium ion, NH3, the ammonium ion plus hydroxide ion. Right. So when you react when you're looking at this, this is a Kb equation, right? Because we're producing base. So you can see here in this particular example, so you end up with your products, again, your ammonium ion hydroxide over your ammonia. So this is because there's 0 milliliters of HCl added. This is just a pure Kb equation where we set up the ice table. We get our ice table, right? And we plug in, I'm not going to go through ice tables, just, you need to recognize, obviously, you start off with, right, the 0.030 molar solution of ammonia, and you'd have to I'm sorry, not 0.03. Let's I'm sorry, 0.05 molar, 0.03. 0.05 molar. So this number here is actually incorrect. This should be 0.05. There should be a 5 there. 0.05 molar solution, because that's what we have here. So we have a 0.05, we have 0 to start, each of these, and you're just simply solving for the x, right? You have x here, x there, and the 0.05 molar minus x on the side here. You make the assumption that the x goes to 0, and then you solve for the hydroxide ion concentration. So that gives you x. That's your hydroxide ion concentration is just right here. And then you plug that into, you can convert that either into, take the minus log of the hydroxide and get the POH, which is 3.02, right? So the minus log of this number gives you a pH of 3.02, and then you calculate your pH to get a pH of 10.98, which makes sense. You get a basic solution because you're adding a base to solution to water. You end up with hydroxide, which gives you a base. There. Where's the 9.5? So that's when you're solving for. So you end up with 1.8 times 10 to the minus 5, which is the Kb, right? So we have Kb, oops, okay, Kb equals 1.8 times 10 to the minus 5, which is equal to x squared over 0.050, and then we rearrange, right, this, I'm sorry, not equals. I'm going to rearrange this to be x squared is equal to 1.8 times 10 to the minus 5 times 0.050. You do the math here, and then you take the square root, right? So then you do x is equal to the square root of all of these numbers. And then that's going to give you the 9.5 times 10 to the minus 4. Make sense? Yeah. All right. So then you just, that's when you solve and then plug that into the log minus log equation to get your pH. The second part, the whole point of this problem was to show that if you, in the second part of the equation, right, where we're adding 20 milliliters of hydrochloric acid solution, we have the example here that in the beginning, right, we're going to have our, this is a limiting reagent problem, right? So before the problem starts, we know that we have to calculate our stoichiometry-based part first, right? So the stoichiometry part goes through and we convert over here. We're going to be converting over to moles, right? Because we have essentially 1 mole reacting with 1 mole to give us 1 mole here. And this is because this is a buffer-based reaction, or reaction with the base, we're going to be reacting the hydrochloric acid with the base, the ammonia. And so we convert over to moles. So just because we added 0.025 molar solution of the hydrochloric acid, and we added 20 milliliters of it, which is 0.02 liters, that gives us 0.5 times 10 to the minus 3 moles of HCl being added. Initially, we're starting again with the ammonia, right? We have our 0.05 molar solution of ammonia. We add 30 milliliters, so we have 1.5 times 10 to the minus 3 moles of ammonia, right? So we know that this reaction is occurring between the two of these. The reason that they use the 0.5 times 10 to the minus 3 here is just to show that this is a smaller number, so you have less acid than HCl, than ammonia. So at the end of the reaction, all of the acid is used up. So you have 0 left. You have some ammonia present, right? Because you're just subtracting 0.05 from the ammonia. So you end up with 1.0 times 10 to the minus 3. And you've shifted the equation over to the right. So after the reaction, you have 5.0 times 10 to the minus 4, which is the same exact thing as 0.5 times 10 to the minus 3 for those of you, paying attention, right? That's 0.5 times 10 to the minus 3 moles, right? That's just this converting directly over to the ammonium ion. All right, so that's after the reaction. So this is the stoichiometry part of the equation that we do first. The second part is we're plugging the numbers into the Ka equation. Right, so we have our ammonium ion, right? So we're going to calculate the ammonium ion, right, dissociates to give us protons plus ammonia. So we plug that into our Ka equation here. All right. And we know that from the, what's the word I'm trying to do? So from the first thing you need to do is stoichiometry, and then we're going to go back and actually calculate proton concentrations after the fact, if that makes any sense. Let me think how to explain this differently. If we go, let me see if I can bring this up in chapter 17. Give me 1 second I'm just trying to find. Here. Let me just 1 second before we continue down this problem. Make sure everybody's on. This was the example that we were talking about. So this is to do with the addition of a strong acid or a strong base to a solution. So what we're doing is basically we're doing a stoichiometry calculation first, right, followed by an equilibrium calculation. That's what's going on in this problem. So that's essentially what's going on in this problem. So if you want to refer back to a section, look at the section here. I'll continue with the problem. All right. All right. So for this problem, one of the things that we need to calculate, because this reaction is the reaction of the inverse of the reaction of a base, right? So we have, this is essentially a base solution where, right, the reverse reaction here is actually a Kb equation. So when we look up in a table, we're going to find a Kb of ammonia. You're not going to find a Ka. You're going to find the Kb of NH3. So you need to solve for Ka of NH4 plus. Right, and then we know that in order to solve for Ka, right, Ka is just going to be equal to the Kw divided by the Kb, right? And that's what this part of the equation is here. Right, so let me blow this up. It's too much. Right. Yeah. It's easier to see now. All right, so we have the Ka. To solve for what Ka is equal to, we just plug in the Kb for ammonia. We have the Kw here. So we have our Ka is equal to 5.56 times 10 to the minus 10. We then need to plug in, right? We know what the Ka equation is because we got that from our overall equation of the reaction. So we need our concentration of our ammonia, right? Our concentration of our ammonia is going to come from the number of moles that we have in solution. Let me change colors. Right, the number of moles that we have in solution right here, dividing that by the total volume of our solution, right? The total volume of our solution is going to be the quantities that we're adding together, right? We have 0.03 liters here, and we're combining that with 0.02 liters. So that's a total of 0.05 liters. So we'll calculate our ammonia concentration there. Our ammonium concentration comes from the 5.0 times 10 to the minus 4, right, divided by that same volume. So we calculate our ammonium concentration. Our proton concentration, therefore, is going to be, right, so we're going to be solving for our proton concentration by rearranging the Ka equation, right? So we rearrange the Ka equation here to solve for protons. So we solve for our proton concentration and plug in, right? So we have proton concentration is equal to our Ka times the ammonium concentration divided by the ammonia concentration. We plug in the concentrations we just calculated previously, and that gives us our proton concentration of 2.78 times 10 to the minus 10. We take minus the log of that, and we get our pH of 9.56. Right. And again, this makes, again, another assumption, obviously, that, that the proton concentration is small compared to the ammonia and the ammonium concentration, which it is in this case, right? Because you can see we're at minus the 10. And when you're looking through and, trying to determine, does this make sense, right? recognize what we're doing, right? In the first problem, we have just base in solution. Our pH in this case is around 11, right? We add acid, 20 milliliters, but not enough to completely consume all of the ammonia, right? So we still have extra base floating around, right? And we still have a slightly basic solution at 9.56. And then the next problem with 60 milliliters of hydrochloric acid, right? Now we're looking at an example where the quantity of HCl that we're adding is going to be exactly the quantity, number of moles of ammonia that we have, right? So in this case, right, the quantity of ammonia is exactly the same as the last one, right? The numbers haven't changed. So our 1.5 times 10 to the minus 3 stays the same. Our quantity of hydrochloric acid is, our concentration times now 60 milliliters. And that just so happens to equal exactly 1.5 times 10 to the minus 3. So from the stoichiometry perspective, all of the ammonia reacts with all of the hydrochloric acid. So after the reaction, we have none of either left. And all of this has been converted over to the ammonium ion, right? So this is just a one-to-one conversion directly over. So we end up with 1.5 times 10 to the minus 3. So this is the equivalence point, right? This is the point at which the proton concentration and the ammonium concentration are exactly the same. So this calculation, when we're doing our doing the math, right? So if we go back, no, sorry, we don't have to do the math. We don't have to go back yet. So now when we're going through, we calculate the concentration of our ammonium ion. Right, the concentration of our ammonium ion is just the 1.5 times 10 to the minus 3. That's that's just the concentration that we have here divided by the total volume. Total volume is different this time because we've added 30 milliliters here and 60 milliliters there. So we end up with 90 milliliters. And so our concentration of the ammonium ion is 0.017, right? We don't, in this particular example, so if we go back up to this problem here for one quick second to see what the difference is at the equivalence point versus when we don't have enough. In the previous example, we knew what our ammonium concentration was, right, because we were left with ammonium ion. In this example, we don't know what the concentration of the ammonium ion is. What we do know is that it's going to be equal to the concentration of the protons. So in this part of the example, both the proton concentration and the ammonia concentration are going to be equal to one another. We're going to be using the exact same Ka equation, right? So I'm going to go back up for one quick second again. Right, so the Ka equation that we're using here is exactly the same Ka equation. Right, so this is still going to be the 5.56 times 10 to the minus 10 is what our Ka is. We're plugging in into the same Ka equation down below. Right, so 5.56 times 10 to the minus 10 is our Ka. The only difference is now our products in this reaction. Right, and if we I'm going to go back up to the equation one more time. That's this equation right here, right? We underlined it, might be easier. Our ammonium ion is being dissolved to give us protons plus ammonia. So it's the same exact equation, and we're plugging it in to give our x squared divided by the concentration that we calculate here. So our x proton concentration here is equal to after we rearrange, take the square root, our x is equal to 3.03, it's 043 times 10 to the minus 6, or 3.0 times 10 to the minus 6. Plug that in to get minus log, and we can see we end up with 5.52, right? 5.52 for our pH, which, if you think about, makes sense. So now we have a weak base, right? We have a weak base, the ammonia, and we're reacting it with an equivalent quantity of strong acid. So the strong acid is going to dominate now, and we're going to end up with a slightly acidic pH. All right, next one, and the last part of this problem is with 65 milliliters of ammonia, HCl being added to this. So in this example, again, our ammonia is exactly the same in the beginning. Now we're adding extra acid. Right? We have more acid than we do ammonia. So after the reaction takes place, right, we're still going to have protons left. We still have protons left. We end up with the same quantity of ammonium ion as we did in the part C. And now, since we're past the equivalence point, we have excess proton. That's going to be the thing that determines the pH. Right. So in this case, because we have extra H+, it's going to be the thing that dominates the entire reaction. The equilibrium that comes from the small quantity of ammonium ion that's present is going to have very little effect on the pH of the solution because it's such a small quantity, right? If we go back, right, because you can see in the previous part of the problem, right, we have a relatively small quantity, 3.0 times 10 to the minus 6 molar protons. Whereas if we come here and we calculate when we have extra protons, right, we have our number of moles divided by the total volume. Again, the total volume is a little different here. Right, we have our 30 milliliters plus our 65 milliliters gives us our 95 milliliters total. So you can see now we end up with 1.3 times 10 to the minus 3 molar, right? So that's a big difference in comparison to the 3.0 times 10 to the minus 6 molar that we have up here, right? It's threefold or 1,000 times more concentrated. So that's why the pH is just purely by taking the quantity of extra acid and measuring the pH of that alone. So that was a long and complicated problem, but it gave lots of different examples. It went through, a Kb equation. It went through a Ka equation. It went through an equilibrium equation. Yes, you can go back and look through the video, unless you have more questions that I didn't explain clearly. But all right, so the whole bunch of other questions. No, Ka, sorry, Annie, I just saw your question. The Ka here is always going to be for the Ka for all of our equations are all going to be the Ka of the ammonium ion. So when we're using Kas, we're using the Kas of ammonium ion. Hydrochloric acid is a strong acid, so hydrochloric acid does not have a Ka. All strong acids are just basically, and the last one, but hydrochloric acid is, because it's a strong acid, it doesn't have a Ka, because if we think about what the equation looks like. So think about what's going on in this reaction. So we have at the end, we have in the flask, we have 1.5 times 10 to the minus 3 moles of ammonium ion. And then we also have 1.25 times 10 to the minus 4 moles of HCl, or H+, right? We'll just call it we'll call it HCl. HCl. Right? We know the upper component of the equation here is going to give us, just slide this down, you know, we know that 1.5 times 10 to the minus 3 moles of HCl, of ammonium ion, is going to give us 3.0 times 10 to the minus 6 molar protons in solution. HCl, on the other hand, is going to be fully dissociated. So what we have, HCl, when you dissolve that in solution, when you have an aqueous solution, it's fully dissociated to give us H plus Cl minus, because it's a strong acid. So the number of moles here, 1.25 times 10 to the minus 4 moles here, is going to be exactly equal to the number of moles here of protons, because it's a single-headed arrow, right? So we have a complete conversion over to H plus, and this is the number. So we don't need a Ka because it's complete dissociation. Whatever quantity of HCl we have is the quantity of protons we have, which is what we plug into the equation here when we figure out our concentration. So the HCl is dominating because, you know, we end up having, you know, 1.13 times 10 to the minus 3 molar solution of HCl. Does that make sense? So what these 4 problems were meant to demonstrate, just for a quick review, is the first one was just a Kb equation, right? The first one was we dissolve a base, ammonia, in water, and we want to know the quantity of, we know the quantity of hydroxide ions that are being formed, right? So we calculate, because this is a Kb, there's no acid present, so we just calculate the quantity of hydroxide, and then we use that hydroxide concentration to calculate pH. And that's because this is just a straight up Kb problem. The second part is what happens when we have a neutralization reaction occur. So it's a stoichiometry reaction followed by another reaction where we're just simply measuring a Ka. And the reason for that is because now we actually have ammonium ions present, right? We have ammonium ions present. So this is a Ka equation. And so that's the one difference here, is now you have both acid, you know, ammonia and ammonium present. So we plug this into the Ka equation, and we need that. We need to use the Ka equation because we're going to be measuring the number of protons that are being formed. The next one looks just like the previous one. The only difference is this is the equivalence point. This is when we have the exact quantity of both acid and base in terms of moles. So this just shows you what happens at the equivalence point. And the last one is what happens when you have extra acid, strong acid present in solution. So there really are 4 completely different problems. And it's just meant to demonstrate what happens when you have slightly different quantities of acid and base being mixed together. You know, they're all under the same problem because they're related, but they're all 4 completely different problems in the way you calculate the answer. And that was kind of the point, is just to get you to see that there's different problems here. So this is a really good one to cover, just from an understanding perspective. Anybody have any other questions on this one before I move on? Let's see. If you understand what's going on here, you're in good shape. If you don't understand what's going on here, you're not in bad shape, because this is, there's 4 complex problems, but it's just definitely one of those things you want to take some time to understand what the difference is. That was the point of this problem, was to get you to understand the differences. All right. Let me go back up and see if there are any other questions up here. Let's see. So I did number 5, number 7. I did 4B and C. Next one is 6A. All right, there's a question here. How do you know that part A is a base reaction? All right, so this goes back to, right, in this example, maybe it's worthwhile. Let me pull up. Give me 1 second. Let me find. So it's a good question, because the base one is something that doesn't come up that often. So if we look at chapter 16, so chapter 16, we talked about weak bases, right? And in chapter 16 here, right? So we had weak bases, where weak bases like ammonia are the reagents that basically, when you react with a weak base, reacts with water, it forms the conjugate acid of the weak base plus hydroxide ions. So you want to be familiar with the types of weak bases that exist, right? A lot of times they're either going to be nitrogen based, so like ammonia. So they have nitrogen with some group. It doesn't have to be hydrogen here. They could be other groups, and we'll show you in a table in a second. They also could be the conjugate bases of weak acids, right? And let's just show you some example, right? So here's the 2 main categories. You have the neutral ones, so the amines. So ammonia NH3 is one example. Methylamine, where we've replaced one of the hydrogens with a CH3, right? And that's going to, again, the key is that these lone pairs that are present on nitrogen act as a base. Hydroxylamine is another one right down here, where instead we replaced one of the hydrogens with an OH. So these are the neutral type bases. They're usually going to be amines. And then again, the conjugate bases of weak acids. So I'll show you in a picture over here, right? So here's a picture of some of these, and this is 16.4. So this table is in the, or a version of this table showing weak bases is in the help sheet that I'll be posting. So you can see any nitrogen-based substance. When you see a neutral nitrogen-based substance, you're typically talking about a weak base. So ammonia forms the conjugate acid ammonium. Pyridine forms this conjugate acid pyridinium. They don't draw it out for you, but it looks just like this. It's just protonated. Right, so it's just a protonated pyridine nitrogen. The hydroxylamine, another one here. There's some more examples on the next slide, right? So the only difference between ammonia and methylamine is just a CH3 in place of the hydrogen. Okay. So just become familiar with this. Then you have, right, the conjugate bases of weak acids. So H2S is a weak acid. Its conjugate base, hydrosulfide ion, right, has a Kb. The carbonate ion, right, it's just the weak, the conjugate acid is the bicarbonate ion. You could basically, any weak acid can be a base. And we talked about this in regards to determining the acidity of various types of salts, or basicity of various types of salts. Right? So any type of weak acid has a conjugate base, and that conjugate base can just be used as a base in solution. So, and the reason you'll know, let me go back to the problem. So if we go back here to finish answering your question. The reason you would know is because when your problem that you'll be talking about, you have some type of base, and in this case, it's not reacting with any acid. So all you're taking into account is the dissolution, the reaction of the ammonia, in this case, reacting with hydroxide, right? So you have ammonia here reacts in water to give us the hydroxide ions over on the right-hand side. So I don't know how to answer your question other than to just say that you have to recognize, begin to recognize that nitrogen-based substances, or, this could just as easily have been, an AClO, right? Which basically would be the ClO minus is your weak base, right? And you would look up in the table, you look up HClO, it's just the weak acid, and you can calculate the Kb of the weak base. Does that answer your question, Catherine? All right, on to number 6. Unless somebody else has another question related to that. What was it, 6? Let's see, what is 6A? All right, so when we're looking at these examples, these are Ksp problems. So we have the molar solubility of, in this case, lead bromide at 25 degrees Celsius is 1.0 times 10 to the minus 2 molar, right? This is just molar, capital M, moles per liter. It says calculate the Ksp. Well, for this particular problem, first you need to recognize that right when you're dissolving lead bromide, you end up with lead 2 ions and 2 bromide ions. Right, so your Ksp equation is going to be lead to the first power and then bromide to the second power, right down here. Get it, just to the second power. When you're working through this problem, right, you have your, let me try to think of how to describe this. We have our table. Unfortunately, this answer key doesn't describe it very well. Let's see. Let's see. It's not gonna, let me just go back here. Just trying to see if I could find a better place to description. All right, so this is one of the examples where we set up our, I guess it's the what do you call it? The ice tables. And we have our ice table where we have our lead bromide. Because it's a solid, it's going to be not present. Right? So we have our ice table here. We have our lead 2+ ions. And then we have our bromide ion here. And we can see that initially we have 0 of the lead and the bromide. We're going to see when we dissolve the lead bromide in solution, we're going to see an increase of X for lead, right? We're going to see an increase of X for lead and we're going to see an increase of 2X for bromide, right? Does that make sense? So and the reason we're seeing this increase of 2X is because we have 2 bromides for every 1 lead that's present in solution. So at the end we have X and 2X. Now we know from this particular example what the molar solubility is, right? So we know that our I'm trying to think about how to describe this. So we know what our solubility of the reagent is in solution. Let me go back here. And that tells us that if you look over here to the left, right, we have our concentrations because we were given the molarity that we have, right, of the solubility. So we know what X is, right, because we know that X is going to be 1.0 times 10 to the minus 2. So in this case, this is going to be 2.0 times 10 to the minus 2. Because we know our molarities, because we know what the molar solubility is. So now we're going to work backwards plugging this into the Ksp equation, where we plug this into the Ksp equation here, right? So we have our lead 2 concentration, maybe our minus concentration, which is going to be squared. And we just simply do the math to calculate our Ksp. Okay, so you just square 2.0 times 10 to the minus 2, then multiply that by 1.0 times 10 to the minus 2 to get a Ksp of 4.0 times 10 to the minus 6. And the reason that we can use the solubility here, right, is because we know the quantity of PBr2 that's going to dissolve. We were given the number of moles, the molarity that's dissolving in solution because we're given the solubility. Does that answer your question, Amelia? Okay. Let's go back up. All right, working now, periodic table, root. Cameron wants to go over problem 13 on chapter 16. You have more related to this first. So 6C. Okay, so 6C. So 6C is a little different from, well, it's not that different. It's actually, it is squared right here already. So the square is there. So, right, there's a square for hydroxide. Is that the question? I'm not sure if that's answering your question or not. I'll give you a second to. So this one is squared. It's set up the same way. So when we're solving here, so this one we're working in the opposite direction because we've looked up Ksp. So the last one we were solving for Ksp. This one we looked up Ksp in a table because that's what it asked you to do. And we're solving for the pH, that saturated solution. So in order to do that, we have to calculate the concentration of hydroxide when we have reached the Ksp, basically. And so when you first do this, right, the first part of this math is going to be 4x squared. Multiply that by another x, gives you 4x cubed. So it is still squared all the way through. And then we're going to solve for x. So you divide both sides by 4, and then take the cube root, and that gives you x here, which is the concentration of, right, that gives you the concentration of your calcium ions, which is x. The concentration of hydroxide ions, on the other hand, is going to be 2x, right? So you take twice 2 times the 0.012. What they actually took was 2 times the 0.017, which is 0.024 there. Right. So they do, for the, because we're working in the opposite direction, you use the square as part of your, to determine what x is. But remember, in the ice table, right, so we have our calcium 2+ and a hydroxide, and the quantity that we start with, right, is 0, 0 plus x plus 2x. So we end up with x and 2x as our quantities. So when we're calculating our hydroxide concentration, right, these are our concentration brackets, our concentration is not squared, it's just 2 times x. So the concentration of hydroxide is just 2 times x. It's not actually x squared. It's x squared. I mean, the squared has to do with the Ksp part of the equation, not with solving for a concentration. And this is the difference between Ksp and concentration solubility. All right. Go back to, oops, the other run. So problem set 16. The question, I can't remember, was question number 13. Right. All right, so this one says predict whether aqueous solutions of the following substances are acidic, basic, or neutral. All right, this is a good problem to work on. So if you remember, this is where you're going to need your periodic table, right? And you need to have memorized the rules, right? When you're looking at anything in group 1, right? Group 1 and group 2 in the periodic table, right? Sodium, potassium, lithium, calcium, magnesium, right? None of these, when they dissolve in water, they remain neutral, right? It's going to give you, those metals are going to, give you a neutral solution. Whereas, once we get to group 3, right? Group 3, the transition metals, and basically all the other metals on the periodic table, they are all going to, react and give you an acidic solution, right? Because you have the aluminum 3+, right? This is going to react with water, right? And it can form these, if you recall, the aluminum OH, these hydrates can basically form, it doesn't have to be 3, but I'm just drawing 3 here, right? Where these are all protonated, positive charges have all been transferred to the oxygen, right? And that basically makes this proton here more acidic, right? Because if this aluminum gives up that water, that hydrogen, I'm just going to draw part of the molecule, right? We end up with this oxygen then goes back to neutral, and we end up with a proton being given off, right? So that's this separation that occurs here. So we end up with an acidic solution because reacting, either group 3 or any of the transition metals, and basically most of the rest of the periodic table with the metals in solution, they are going to give off protons when they react with water. Chloride, in this first example, is going to be negligible, right? Because, right, HCl dissociates completely to give us protons plus chloride, right? Because this is a strong acid. So when you dissolve chloride in water, this reaction is never going to go in the reverse direction, right? That will never happen. So you're never going to create any acid from chloride. So chloride has no effect whatsoever on solution. So aluminum chloride gives you an acidic solution because of what's going on the right-hand side here. Sodium bromide, right? Sodium is a group 1 metal. So the same thing here. So since sodium is a group 1, it doesn't form this complex like aluminum does with water. So there's no effect on pH from sodium. Bromide is the same thing, right? HBr, another one of the strong acids. So it's going to have the exact same effect as the equation up here with the chloride. So it's also not going to have any effect on pH. So you end up with a neutral solution here because neither of these are going to form any protons or bases with water. You're asking me what my favorite color is, Jason? You're talking about for writing? That's funny. All right. Let's set that up just a little bit. Then we have sodium hypochlorite, right? This is bleach. Well, we know we've already discussed the sodium ion, right? Sodium ion, because it's a group 1 metal, is not going to react with water, so it has no effect on pH. Whereas the hypochlorite ion, right, that's the conjugate base of HClO. So we know that if we react, right, ClO minus will react with water in equilibrium fashion to give us HClO HClO plus hydroxide ions. Let me draw it the other way. So you can see when we dissolve the conjugate base of an acid, a weak acid in solution, we form hydroxide ions, and these hydroxide ions give us a basic solution. The next example is the CH3NH3 NO3, right? So this is when you needed to, this is going to take a little practice getting used to, and this is one of the things I want you to look at in regards to the base table that we described earlier. CH3NH3, and I'm going to jump over to that table just so everybody see what I'm talking about. The reference sheet. This is important for you to recognize right here, so everybody's hopefully paying close attention. So if we come back to, where is it? Oh, I'm sorry, here he is, right here. So if we're looking at this base table here, right, we have methylamine, right? We have the methylamine here. Unfortunately, I can't write on this. Let me copy this. Oh, never mind. I'll just do it right here. Right, so you can see the methylamine. Hopefully everybody can see the pointer here. Methylamine CH3NH2. Everyone hopefully sees CH3NH2. I'm going to go back to the other slide to show you what's going on here. Right, CH3NH2 is the base. Remember in the problem it says CH3NH3. So recognize this is the base. It has a Kb. Now if we go back to the problem, there we go. Huh, that's strange. Right, so we have CH3NH3 plus, right? That's where the CH3NH3, you needed to recognize that that came from CH3NH2, right? When that reacts, that's the base that can react with water in an equilibrium fashion to give us CH3NH3 plus hydroxide ions. All right, so you can see that CH3NH3 is the conjugate acid of the base CH3NH2. Right, so when we're looking at this reaction, I mean this compound here, the CH3NH3, that we have to say, well, CH3NH3 is actually a positively charged ion. And you needed to recognize that because the NO3 is the negatively charged ion here. So that's the counter ion. We'll talk about that in a minute. So this will react with water separately in an equilibrium fashion to give us H3O plus CH3NH2, right? So you can see when we take the conjugate acid of a base and we dissolve that in water, it's actually an acid, right? So the conjugate acid is an acid itself because it produces protons or hydronium ions in water. So that's going to create an acidic solution. NO3, right, is the conjugate base of HNO3. And HNO3 is one of the strong acids, so there's going to be no effect from HNO3 on the acidity. So it's no effect because it's a strong acid. So this overall solution is just acidic. And then the last problem down at the bottom, where we have sodium sulfate. Right, so the sodium ions we've talked about before have no effect at all on the solution because they're group 1 metals. Sulfate, again, is the conjugate base of H. It's actually the conjugate base of HSO3 minus. Quite honestly, this is wrong, so it should be HSO3 minus. And so this is going to be an acidic solution, right? Because, I mean, a basic solution, because SO3 2 minus will react with water, right, in equilibrium fashion to give us SO3 minus plus hydroxide ions. Right, so this produces base in solution, and that basic solution is right there. Any questions on this problem? Go back and look at questions. So qualitative analysis is the next one. I'm just working down the list. I'm going back up. And so the next person was asking about qualitative analysis. So I give, I can't remember if I have one in problem set 17. Yeah. So here's a problem set 17 is a sample qualitative analysis, right? Problem where you have to work down the list, right? You're going to be working down, and it's kind of hard for me to work through the entire sheet, but this is a sample qualitative analysis where and this goes through and talks about what this possibly could be in the description right down below. I don't know if that's, yeah. I'm not sure if this is what, Sophia, you would ask about qualitative analysis. So you basically have to work through the list similar to this.
So we could see something like similar to this, like a test.
Yeah, it could be something like this, or something simple like, you have to distinguish between a couple different compounds and determine which one's in solution based on the qualitative analysis. Let me, like, let's say, for example, I haven't actually written that part of the test yet, so that's on my list of things to do. Let's see, chapter 17. So if you look here, come on, hold up. Right, so if I asked you to, come up with a test that's going to differentiate between, if I say determine whether or not you have lead ions or chromium ions in solution, right? And you could see that, lead sulfide precipitates here, whereas the chromium is precipitating out down here. So you could come up with a sequence that showed that if you add hydrogen sulfide to the solution with 2.2 molar HCl, and you see a precipitate, you would assume you have lead. Whereas if you didn't see a precipitate, but then if you add ammonium sulfide at a pH of 8 and saw a precipitate, then you'd assume you have chromium. So you see how you can use the table, something along those lines. The practice problems, there were a few practice problems. Most of the ones were not related to the stuff that we were going to have on the exam. That's why I didn't cover them. From time constraints. Except for, I think, the first one, but that was a pretty simple one. Sorry. Let's see, next problem. Let's see, where was I? I'm just working down the list. Number 9 on problem set 17. Here we go. Oh. Which is this one. All right, so Brian, this is the one that we were just basically discussing. You're going to be following through that qualitative analysis. And you would see that if you have all of these possible, these are the possible salts that you have in solution here, right? And what you would try to do, and what you're going to be doing, is you would look through the sequence. You have this unknown solid, and they tell you in the first part you add dilute HCl, and you have precipitate that forms after you filter. You know, because they're trying to figure out which one of these is completely soluble in water, right? Which of these, all of these different compounds, is completely soluble in water. And there's obviously you need to go through and understand, and you're basically looking at the different groupings that are in that qualitative analysis table. Let me see if I can paste that over here. That'll work. Might be easier. There we go. Oops. That didn't work as planned. All right. Let's just look at this problem here. All right. So here we go. So if we have dilute HCl, right? You're at an HCl solution here, and you form a precipitate. Right. So if you're paying attention here, so if we're adding HCl to the solution, right? We add HCl to solution, we're going to see a precipitate with silver chloride, lead chloride, and this mercury Hg2Cl. So we can see that more than likely, because remember, we have lead ions present in solution. So lead is going to come crashing out of solution in that first step. We also so we know that that's going to be one of the problems, one of the things that's going on here. The other thing they talk about is, and I'm not going to be asking this table this type of question, but this, if you recall, last semester we talked about the solubility of various types of salts, and I'd have to have that table incorporated there. But cadmium sulfide and mercury oxide are two compounds that are not soluble in water, so they're initially ruled out as well. So these two are ruled out based on what we learned from last semester. So the first thing that happens is the lead nitrate forms the lead chloride and comes crashing out of solution. So we know that this is not one of those substances then when we add the H2S, right? H2S at pH of 1, because it's under acidic conditions, indicates that the cadmium nitrate is going to become crashing out, because you can see the cadmium is right here in the table. So we know that the cadmium nitrate comes crashing out of solution because it forms the cadmium sulfide. We could also see and then the next one they talk a little bit about the lead sulfide here. Then when we add H2S or some other sulfide at pH 8, they're basically talking about the fact that nothing comes crashing out, right? When we adjust to pH 8, there's no precipitate that forms. So you can see that that has none of the salts in the group that we're looking at. Then we have the next step. Right, this shows us that, because of that, the zinc sulfide should have come crashing out. So this tells us that we don't have any zinc sulfate in solution. So that's not even present in solution here, because we would have seen a precipitate come crashing out of solution. And then the last part goes through, let me see. I'm just trying to walk through. And then we add addition of ammonium hydrogen phosphate, and you can see that's this part here. And we have no precipitate, so that shows that we don't have any of these ions present in solution. And then the last, it says the remaining solution shows a yellow color in the flame test. And we talked about this very briefly last semester, but the yellow color in a flame test gives you the presence of sodium ions. And so this overall tells you that you have lead nitrate in solution, and you definitely have sodium sulfate present in solution. The cadmium nitrate is probably present because it showed up here, right? Because more than likely this is the cadmium that shows up here. So, and we know based on this, all these others are not soluble here. I don't know if this answers your question. Hopefully it helps you understand how to use the table, but you're basically looking at how things dissolve, how things precipitate from solution when you add different substances, right? Everybody understand how to use this table, right? Or you could use this various ways, right? I could also say, okay, you have a solution of an unknown ion, some unknown metal ion, who knows what the charge is, some number charge, and try to determine whether or not it's, like I said earlier, if figure out whether or not it's chromium or tin. So you would be able to, distinguish by creating a test to, test between the two of them. Yes, it's only cations you can identify with this chart. Correct. You could probably create something for anions, but that's not as common. Any other questions on that? Let me go back and look, see what else is next. So we got, that was Annie, had the same question. So for Ksp, that doesn't help. That's not for this table. Yeah, that's just for this table. Correct. There you go. Other questions? Been on for a while. Hopefully people will benefited. I think if I haven't answered your question, please repost it because I missed it in the list. I was opening up the test at 8, but I can open it up earlier if you want to start earlier. My guess is, most people aren't going to be racing to get up at 8. So it's open from 8 till 11:59 because that's what's required by Canvas. So you have 4 hours to work on it, which should be plenty of time. It's probably going to be somewhere around 15 questions or so. I hope it doesn't take 4 hours, but my guess is there are probably people who will take the full 4 hours. My exams are always similar to problem sets and practice problems, Sophia. I don't try to trick you. Any more questions? All righty. So the session is recorded, so you feel free to come back. Can you take stretch breaks? Yes, Brian, just like you did last time. When you get up to walk around, just tell the computer that you're going to get up. People did that to go to the bathroom. It records that you disappear, and it notifies me. So it's one of the. Oh yeah, if you're going to wear a baseball cap, wear it backwards. I don't know. That's the only other thing. Let's see, is he still on? No. So it's the only other thing. Just wear a baseball cap, wear it backwards. Do I actually have to watch the recordings? No, but I don't watch the recordings there, except for their system lets me know when people aren't sitting in front of the computer or are staring off into the distance or doing something that looks like they shouldn't be doing. It's artificial intelligence. So then I just look at those small little sections if I need to. Some people just trigger it more often than others, and other people have no triggers whatsoever. So I actually know, it would kill me if I had to watch the entire video of everybody, right? 2 hours, 3 hours for my entire class with the people. I'd be sitting in front of my computer. That would be awfully boring. No offense, I think you're all wonderful and beautiful people, but I don't really want to sit there and watch you on video. You're not an actor or an actress yet. Didn't like your face. It could be just lighting. I don't know. You take offense to that. All right. I'm gonna stop the recording.